Hello, welcome to our fourth tutorial on Sequential Monte Carlo samplers, brought to you by the Centre for Doctoral Training in Distributed Algorithms at the University of Liverpool. And in this video, we are going to start to talk about how we can find the optimal L-kernel for our Sequential Monte Carlo sampler. Okay, so the story so far is at iteration 1, we've generated samples of x. So iteration 1, we've generated n samples of x, so the superscript denotes the sample number, and we have I is equal to 1 from 1 to n. We then calculate the importance weights, which is just standard importance sampling, i.e. target distribution divided by proposal. We've then generated a second set of samples, so iteration 2. We have another n samples that are generated from this distribution conditional on our first set. So perhaps, for example, we're hoping that this second set of samples is going to be closer to the regions of probability mass in the target. And now the importance weights of our ith samples from iterations 1 and 2 is given by this equation here, which we derived in the previous video. So you can find weights at iteration 2 from weights at iteration 1. But now we have this L-kernel, and it's up to us to decide what the L-kernel actually is, so long as it's a valid probability distribution. So first, we will look at one possible choice of L-kernel that we might decide to go for, but which actually turns out to be a bad idea. So let's just say, to keep things simple, that our proposal distribution at iteration 2, so argument x2 conditional on x1, let's just say that we've simply got a normal distribution, argument x2, and let's say that it's centered on x1, so the mean is x1, and it has, so let's keep things simple. So let's say we have a one-dimensional x, and let's just say this has variance sigma squared. Okay, so now we might think an L-kernel, suitable L-kernel, might look a bit like this. So it's now the argument is x1, and it's conditional on x2. But let's say we're going to also set that equal to a normal distribution, only this time the argument is x1, and we're going to center it on x2 and give it the same variance sigma squared. So why might we do this? Well, it might be obvious already, but if we just do a quick drawing down here, so I'm going to put a vertical axis which represents probability density, horizontal axis which represents x. So if we draw, let's say that Q2 looks a bit like this, and that it is centered on x1, as that's the mean. And then let's say that the L-kernel looks a bit like this, and that this is, of course, centered on x2. So now note that if we look at the proposal, that's Q2, the probability of x2 conditional on x1 is then going to be given by basically the value of the red line at this point. Likewise, if we look at the L-kernel, the probability of x1, if it's centered on x2, is going to be given by the height of the line here, which, if I draw them properly, is equal. So that means that for all of your x1s and x2s, the ratio of the L-kernel to the proposal will cancel. So that sounds like it's good. Why? Because then it means that this term here can simply be equal to 1. So you can just select that and delete it, and then move our weights over here. And now things look a bit simpler. As at iteration 2, all we need to do is calculate this ratio here and multiply it by the importance weight of our samples at iteration 1. If you're used to Markov chain Monte Carlo, specifically the Metropolis algorithm, this approach might seem attractive also because this looks very much like the Metropolis acceptance reject ratio that you calculate as part of that algorithm. However, while this does look very convenient, it's actually suboptimal, and you can get better performance out of your sampler if you choose a different optimized L-kernel. So what we'll do next is we'll go through some maths to derive what the optimal L-kernel really should be. So firstly, we need to remember basically what the overall objective of our sampler is. And once we've written that down, then we can write down the L-kernel that optimizes that objective. So just as a reminder, ultimately what we want to do is we want to estimate this expected value of some function of x, which is equal to this integral of f of x multiplied by the target, or with respect to x. So ultimately that is what we want to find. At iteration 1, we're going to realise this estimate of our expected f. So I'm going to write an f with a tilde on top of it, so that means it's our estimate. At iteration 1, we realise this using standard importance sampling. So it's equal to this 1 over n summation of our importance weights, so that's weights of our first samples, multiplied by this function that we're interested in, evaluated at that sample. And so that is our standard importance sampling estimate of this expected value of f. At iteration 2, so this is our estimate of f at iteration 2. Again, it's another Monte Carlo style estimate. So we have a 1 over n, it's the summation over all of our samples. Now we have our weights at iteration 2. Now, of course, we have samples of x1 and of x2, multiplied by the function we're interested in at x2. So iteration 2 of our algorithm, this is now our estimate of the expected value of f. Now the key thing to remember is that x1 and x2 are random variables, are samples of x1 and x2. So we could do this experiment lots of times and get different results, i.e., in other words, our estimate f2 is also a random variable. So we think that this estimate is unbiased, so the mean of this random variable is equal to the thing we're interested in, the expected value of f. But what we want to do is we want to make sure that the variance of our estimate is as small as it can be. So now we're moving towards an objective for our L-kernel. We want our L-kernel to minimize the variance of our estimate. Again, just remembering that our estimate is itself a random variable. So specifically, we want to minimize the variance of our estimate at iteration 2, which is, of course, equal to the expected value of our estimate squared minus the expected value of our estimate all squared. So what we're going to need to do next is write down an expression for f2, and calculate these two terms, or derive expressions for these two terms. And then we'll try and minimise that with respect to the L-kernel. So I'm going to move this over here. Now we're just going to replace our weights iteration 2 with this expression from the previous video. So just moving f. Like I say, we're just going to remove this and replace with this. Okay, so that is our expression expanded for our estimate at iteration 2. Now I'm going to replace the weights at iteration 1 with this expression. So we remove, or just move this to the side. I'm going to delete weights at iteration 1, replace with this. Okay. So now straight away we can see that we have some terms that will cancel, i.e. these two. So then finally, zooming in down here, so we can remove this and this because they cancel. Then just tidying up. We've now substituted both of our expressions for the weights into here. So now we're going to write down the expected value of this, given that it's expected with respect to samples from the proposal. So we need to be a bit careful with our notation here as we're now integrating over x1 and x2. So we're going to say that the expected value of our estimate is equal to, so first of all we need to note that the 1 over n and the summation come outside of the integral. Then, like I say, we now have our we're integrating over x1 and x2. So let's write pi of x2, and then there's our L-kernel, x1 given x2, divided by, then here we have our proposal, which is q of x1, then q of x2, x2 conditional on x1, and then still have our f of x2. And then you have to remember that let's try and draw that properly. You have to remember that our samples are coming from the proposal in this case, or our expectation is taken with respect to the proposal. So we're going to also have a q of x1 and our q of x2, x2 conditional on x1 here. And then we finish off the integral, as I say, by saying it's with respect to x1 and x2. So firstly, we note that we're basically adding together the same thing n times and then dividing it by n. So straight away we can get rid of all of this stuff. We then notice that the proposals on the numerator and the denominator, so we can get rid of this and we can get rid of this. Okay, so things are looking a bit simpler. Now this integral is, let's take it with respect to x1 first. Well, this is the L-kernel is the only thing in there that is a function of x1. So if we just zoom in slightly, and the L-kernel is a probability distribution, or probability density function, I should say, in this case, as it's continuous. So if we integrate with respect to x1, then we can get rid of this stuff as well. So now there's not much left. In fact, there's not enough left for us because we've completely got rid of the L-kernel. And what we have really is we've just showed that our estimate should be unbiased, i.e. f2 is a random variable, our estimate of f at iteration 2, but on average it should be equal to the true expected value of f that was the aim of the algorithm, basically. So after all of that, what we've discovered is that this term here, this second term that we're looking at, actually is not a function of the L-kernel. This expected value of our estimate at iteration 2 is not a function of the L-kernel, so let's get rid of it, basically. And what we're going to say is that that is just some kind of constant. So just to be clear, we're saying that this is a constant basically because it doesn't change with the L-kernel. And actually what we're interested in doing is choosing an L-kernel that minimises this variance term. Fortunately for us, we do have this second term here, which, as it turns out, does change with our choice of L-kernel. So that's more maths, obviously, and probably too much for this video. So I think we'll stop there, and then in the next video we'll pick up by trying to derive an expression for this term and then minimise it with respect to the L-kernel.